Okay, so let's talk a little bit about how to solve an NMR problem. Let's just say, for example, you know that in your mass spec, the molar mass or the M plus ion equals 86. And the other thing that you know is that your molecule only contains carbon and hydrogen. How are we going to figure out molecular formula if we're given that kind of information? So how would you solve that problem? So there's a couple different ways you can do it. You can just do it by trial and error, and that would probably be simple enough. There are some equations that are a little bit of a shortcut. If you only have carbon and hydrogen, here in step 2, you can see we can write the equation 12x plus y equals your molar mass, where x is the number of carbons and y is the number of hydrogen. Of course, 12 is the molar mass of carbon and 1 is the molar mass of hydrogen. So that's where that equation comes from. If there's also oxygen in your compound, you can use the equation 12x plus y plus 16z equals your molar mass. And of course, z is the number of oxygens, and the molar mass of oxygen is 16. If there's nitrogen in your compound as well, remember your molar mass will be odd if there's an odd number of nitrogens. And second of all, we can use the equation 12x plus y plus 14a, where A is the number of nitrogens. And of course, the molar mass of nitrogen is 14. And if you have a bromine, we have 12x plus y plus 79b. That's going to be equal to the molar mass. So the next step after we come up with what equation we're going to use is to figure out how many carbons. And so once you estimate the number of carbons, you can start using algebra to solve your equation and then ultimately check your answer. So if we go back to that original problem where we have only carbon and hydrogen and a molar mass of 86, the way that we're going to solve this problem is 12x plus y equals 86. So we're going to use that equation. Now the next step is trying to figure out how many carbons there are. So we can estimate that. In a molar mass of 86, we could either have 6 or 7 carbons. Now 7 carbons equals 84. The problem with this is there's no way to combine 7 carbons in a molecule and only have 2 hydrogens, right? Because if you take 86 and 84, the difference would be 2. So that would mean that we only have 2 hydrogens, so that's not going to work. What we're going to do instead is use 6 carbons, and then we're going to go ahead and use the algebraic equation of 12x plus y equals 86, and we're going to substitute in 6 for our number of carbons and set it equal to 86. So it turns out that y equals 14. So if that works, we'd have C6H14. The first thing I do is make sure that makes sense in terms of degrees of unsaturation, and it does in fact make sense. And so that is our answer, C6H14. The second example is we have a molar mass of 100, and this time we have carbons, hydrogen, and a single oxygen to equal this mass. So we're going to use the equation 12x plus y plus 16. Okay, so we're going to use 16 here because we only have 1 oxygen. And we're going to set that equal to the molar mass, which is 100. And we're going to simplify the equation. So we're going to subtract 16 from both sides. So we have now 12x plus y equals 84. And so now we have to determine the number of carbons. Again, with 84, we can either have 6 or 7. And if we know that 7 carbons would equal 84, then there's no room for hydrogens. So we need to think about using 6 carbons again. And so if we set that equal to 6 and we solve our problem, we see that y, or the number of hydrogens, equals 12. And so our formula will be C6H12O. So that's one quick way that you can determine the formula based on just the molar mass and knowing what's in the compound. Now, if we go through and start talking about fragmentation and trying to figure out how a molecule will fit together, let's go ahead and look at the mass spec for pentane. So here's the molecule pentane. And let's see how this breaks up and how it makes sense. If we jump right down to the mass spectrum at the bottom, we see here that the parent ion, or the M plus, is at 72. So we know that 72, and that makes sense because pentane is C5H12, and that equals 72, so that works. And if you wanted to see what that looked like, it's actually shown right up here. that is the parent ion. It is ionized and it is a radical. So we have a positive charge and a radical. And that's why we can visualize it in the mass spectrum. And so if we look down to our next big peak, which is the one right here, which is at 57, we can take the difference here between the 72 and the 57, and that difference is, as indicated here, 15. But 15 is the loss of a methyl group. And so up here at the top, you can see here is what's visualized in the green, and then here's what's lost. And so minus 15, carbon plus 3 hydrogens is 15. And so anytime you see loss of 15, it means that a methyl group fell off or a methyl group was fragmented off. If you take the next step and talk about the distance from 72 to the base peak, okay, so the base peak is the tallest peak, so that's right there. So whenever you're solving these, you're always going to want to label the base peak. And actually, let me go back, and we're always going to want to label the M plus peak as well. So if we take the difference between the parent peak and the base peak, we end up with a value of 29. And so what is responsible for that base peak is a molar mass of 43, which is this compound right here shown in the green. And what is lost is 29, which is shown right here. And it's a CH3CH2. So we know our base peak is this propyl group. And so now if we take it one step further and say what happens when we go from our parent ion all the way to this other large signal, if we take the difference between 72 and this peak right here, which again, you're going to start becoming very familiar with these regularly occurring numbers of the 29 and the 15 and the 43 and the 57. So if we go to this peak right here at 29, we see that we have visualized the ethyl group and we have lost the propyl group. And then we can go one step further and we can talk about the difference between 72 and this other peak right here, which is at 15, where we've actually maintained the methyl group and lost the butyl group. And so I hope you can see that because we have taken off one methyl group at a time, 1, 2, 3, 4 from our pentane, we know that it has to be a straight chain. So now you know my thought process. Let me now show you how I would like you to present your answer. So if we're talking about your peak at 57, I would draw the molecule. There's our pentane. And what's happened for the peak at 57 is that we have in fact broken this bond. So this bond right here has been broken. And so on this side, we have a methyl group that is just a radical. And on this side, we have CH2, 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 CH3 that is a radical cation. And so by simply drawing this right here, we see that we get two fragments, and the 57 is here and the 15 is here. So that notation with the little Z to indicate our fragmentation is the notation that a mass spec expert uses as well. If we start with 2,2-dimethylpentane here, and we're going to see our base peak is going to be this fragment right here, where we have loss of 43 and we are left with 57. So we will see a base peak at 57 and loss of 43. So of course, what's shown in green, the most stable carbocation, is going to be the thing we visualize in the spectrum. And so if you're given a problem where you know there's 7 carbons to start and this is your most stable carbocation, then that gives you an idea that there has to be this tert-butyl group. This is how we kind of put things together to solve a mass spec problem. So since the tertiary carbocation is much more stable than a primary or secondary, this peak that observes the loss of 43, which would be a 57 molar mass, is going to be the base peak, is going to be the most abundant. And here's a table that summarizes some of the common fragments that are observed in mass spec. If you have loss of 15, that's going to be a methyl group. If you have loss of 29, that's going to be an ethyl group. If you have loss of 43, that's going to be a propyl group that's lost. If you have 57, that's going to be butyl. And then again, remember from the previous video, when you have loss of 18, that means that you had an alcohol and you have loss of water. And so this is going to be helpful to get these numbers in your brain and just kind of memorize these. And so here is the mass spec of C5H12. And so this is what you might be given on a problem set and or on that final project at the end of the semester. Our molar mass, or our parent ion, is 72, and so we can start labeling right there. This one right here is going to be our base peak, so that's pretty straightforward. And we see right here from 72 to 57, we easily see loss of 15, and so that means there's a methyl group. And then from 72 to the base peak right here, we see loss of 29, which is an ethyl group. From our parent molecule to our 29 right here, so this is 29, and so we have loss of 43, which is a propyl group. And then we can look at that one right there as well. So we have from 72 to 15, we have loss of 57. So in this case, we've actually just done this problem. And so in this case, we have pentane. And if we were to describe exactly what was happening at this peak right here, we have pentane and we have cut right there. And this is going to be minus 15. And what we have left is 57. And at this base peak right here, we have pentane again, but now the cut goes here. And so we have lost 29 and we have 43 left. And at this peak right here, we have pentane again, and we've cut right here. And so we have lost 43 and we have 29 remaining. Okay, and then same with this one right here. We can cut right here, and so we have 15 and we have lost 57. And so this is how I would like you to describe your mass spec problems when you're solving them. First thing is you have to label the parent peak, you have to label the base peak, and then I want you to indicate the fragmentation using this notation with the Z's for the cuts for all major peaks. Now if we go to the next problem, it also has the same molecular weight, but we see a different fragmentation pattern. And so this one, we will have to try to figure out how this goes together. In the previous one, the fact that we had strong peaks at all 4 of these fragments meant that we had to have a straight chain. So this one right here has the same molar mass. And so we have the 72, so that's our M plus. And our base peak is also 43, which is the same as the previous one. But now this time, this 57 peak is very large. So we have loss of 15. So this tells us that when we lose a methyl group, we have a very stable species. Whereas in the previous one, when we lost our methyl group, this one wasn't very abundant. So that wasn't very stable. But in this case, when we lose a methyl group, we have something very stable. And so we're thinking that probably we might have a secondary carbocation when we lose 15, or even a tertiary. And the same with the base peak. When we go from 72 to 43, we lose 29, and we have 43 left. This one we have 57 left. And so we're trying to imagine a molecule where we could lose a methyl group or an ethyl group that would both give us a nice, stable species. And so I'm going to go ahead and show you that we could put the molecule together like this. So instead of being the straight chain, now we have this C5H12. So I have 5 carbons and 12 hydrogens. And look at this. If we take this methyl group off, what do we have left? A secondary carbocation radical. And if we take this ethyl group off, minus 29, what do we have? A nice stable carbocation radical. I hope this shows you how you can distinguish based on the fragmentation. When you have both of these species, both the 43 and the 57, are stable species, then that's probably showing you that they're a secondary or tertiary carbocation. So you have to think about putting it together differently. Now, in the homework problem, you'll see that I give you other information. For example, wouldn't it have been very helpful if I told you that in terms of carbon NMR, this molecule here gave us 4 signals. And if I went back here and said with this molecule right here, there were 3 signals. And so you'll be given additional information. Sometimes mass spec all by itself can't really solve the problem, but I'll give you enough information that you'll be able to solve it. If we go back and look at C5H10, the first thing I do, which I forgot to tell you on the previous one, is I calculate the degrees of unsaturation. C5H10, we're going to see that we have 1 degree of unsaturation, and so that's going to help us as we move forward. And if we look at our molar mass, it is 70, just like is indicated at the top here. So we have a molar mass of 17, that's our parent ion. And if we look right here and we go from 70 to 55, we see a loss of 15. So we see a loss of a methyl group. And then if we also see here, so if we look at our parent ion and we see right here, loss of 28, our base peak here is 42. This is curious, right? Like, how is this going to actually work? So this is the spectra for cyclopentane. And so the fact that our base peak is 42 means that we had to have 2 cuts, one here and one here. And so instead of being 43, it's only 42 because we have a hydrogen missing at each one. So the fact that we have 42 as our base peak tells us that 2 bonds needed to be broken so that we could get to our 3 carbon fragment. And if we go to an isomer of that, again, C5H10, so we have 1 degree of unsaturation, and we look at this species, we can see 70 is our M+, so that's good. And now we see our base peak right here, and now our base peak is at 55. So how does that work? Okay, so we know we have 1 degree of unsaturation. Our base peak is at 55. And so we need to figure out a way that we could have moved a methyl group, because loss of 15 is the biggest peak. It is the base peak. So we're going to be pulling off just a methyl group. So you could probably imagine a couple different scenarios. Like, I'm even thinking we could have a 4-membered ring with a methyl group off and break that. But it turns out that this is actually a spectra for this compound. And so this is the methyl group that breaks off. But again, without me giving you more information, you might not be able to distinguish those two, except for the fact that this is also a pretty strong peak right here, which would be this cup. So here's another example of C5H12 that I'd like to do. This one does not show, but we have our parent ion at 72. So we can maybe put that in here. Here's our M+ right there. So the base peak here is 57. So try to imagine a molecule with 5 carbons where we remove a methyl group and get our base peak, which is very stable, 57. And so this is one we've actually seen before. So we can just cleave this one off right here. And so that's minus 15, that's minus a methyl group. And what do we have left? We have this tertiary carbocation radical, which indicates that base peak. So sometimes it's pretty straightforward, but other times you definitely need more information. And so real quick, here's a table that talks about isotopes in terms of these high resolution mass specs being able to give us more information about all of the isotopes. And so there's this table where we have the mass of a proton, the mass of a deuterium, and a mass of a tritium, and then we have carbon 12, carbon 13, and carbon 14. And so we can really use the natural abundance of these isotopes to really pinpoint the exact mass and the difference between some of these ones that would ultimately, C5H80 and C6H12 both have the general molar mass of 84, but using the isotopic distribution, we can really pinpoint and know exactly which compound we have. So that's all I have for mass spec. The problem set is going to be a little challenging, but work through it and see if you can't come up with a description using this notation where we use the Z to cut the bonds And I think it's important to make sure you know the difference between what is lost and what is visualized. Okay, mass spec, there you go. Good luck.